Hi everyone, welcome to lecture 6.1, 6.2. So today we're going to talk about kind of a new chapter using definite integrals to compute all sorts of geometric things. So we've learned a bunch of these different methods of actually doing integrals, but we can find volumes, we can find masses, we can find total work required to move an object. We're going to imagine shapes that are built out of volumes sort of sliced up in different ways, and it's going to be pretty cool. So this is kind of one of the main points of the course is we can use calculus to, find the volume of a sphere, for example. Like you might remember from like geometry that the volume of a sphere is 4/3 pi r cubed. So where does that formula come from? No idea. One way to show that it's true is uses calculus. So that's just an example. Kind of the main reason people even care about calculus is they want to do physics, they want to do engineering, they want to find work, they want to think about things like heat and magnetism and stuff like that. It turns out, especially as the calculus gets more advanced, you can use integrals for all these things. So we're just going to kind of have some sort of straightforward like geometry stuff to kind of start towards that path. So a good one to think about is the area between two curves. So I just want to draw a little picture. I mean, we already know, right? We already have a pretty powerful thing, which is that the integral can find the area under a curve, so between the curve and the x-axis. So it turns out that a pretty easy, actually, extension of this is to imagine we have like two curves, and instead of doing the area between this curve and the axis, I'm going to do the area between one curve and another curve. So it turns out this is pretty easy to do once we know how to do this one, which we already do, and that kind of really expands your vocabulary, right? Now all of a sudden, if you have any sort of imagine you had some sort of weird shape or something, and for some reason you were interested in finding the area of this shape, you'd have to be a little clever with splitting it up and stuff, but you could do like this idea of integral between two curves to find the area of the shape. This example is actually kind of annoying the way I drew it, but if you imagine like just kind of big picture, imagine if I like sort of like cut it right here and like kind of drew some like XY axes right here. Imagine like introducing XY axes. Suddenly I can see this as like a region between two curves, a lot like this right here. And so if you could sort of write down equations for those things, then you could find areas. That example is a little weird. I was trying to be a little too general. You might have like an arc of a circle or something like this. So here, as long as I can see this as like a top function and a bottom function, then I can use the method we're going to use to find the area between these two curves. Okay, so let's see how this is going to work. The basic idea with this one and with all of them is going to be whenever you want to add up a bunch of small things to get the total thing, that's when an integral can help you. So for areas, right, I kind of hinted when I was drawing at this already, I have, like at every x value, I have sort of this vertical slice. And I can sort of imagine that if I add up all the vertical slices, like all infinity of them, then that sort of like fills out the area, is sort of the idea. To make that precise, we do the Riemann sum thing, right? We add up the rectangles, but you can kind of think of it as adding up these little slices. Volumes and masses of 3D solids. So, for example, if we have like a cone shape in 3D, you know that each of these cross sections of the cone is a circle. So in much the same way as we added up these vertical lines to get the area, we could imagine adding up the surface area of all these circles, and it'll get the whole volume of the cone. And there's lots of 3D shapes you can do like that. Like for example, you could have a box, a rectangular solid sort of shape, then each slice is a square, and you could add up all those squares. You do a sphere, each slice would be a circle, just like with the cone. You'd have to think a little bit. It can be a little tricky. Like here, the circles, they change size as you move up and down. Here, the circles also change size, but like in a different way. Here, the slices are squares, which don't change size. So there's some details that we'll get to. But that's the basic idea. Similarly, total work. We'll talk a bit about this, but if you know a little physics, you can like have a little bit of work, and then to move something a short distance, and if you take a little work to move it a little distance, and another little bit of work to move it another distance, you can kind of add up all that little bit of work, and it'll be like the total work is the idea. So anytime you're adding up a bunch of small things. Okay, so let's look at area between curves. So I said it was just a straightforward sort of extension of what we know already. So let's just look at this example. So I have two functions, 5 minus x squared and x squared minus 3. So I'm going to draw them. So something like this. 5 minus x squared will look something like this, and x squared minus 3 will look something like this. My picture's not perfect. We want the total area, right? Just like when we did the area under a curve, we can imagine like chopping up this area under between the two curves into a bunch of rectangles. So something like that, right? More and more rectangles. And if I focus on like one of these rectangles, that made an arrow. Sorry. If I focus on one of these rectangles, I can think about the dimensions of that rectangle, right? It's at its left endpoint here is maybe at a position x. The height is the most important thing, right? I guess the width here, it would go over to x plus a little bit, x plus delta x. So the area of one of these rectangles is the width, which is delta x, times the height. And what's the height? So area equals, what's the height? Well, I called this top function f, and this bottom function g. So the top height value here is f of x, and the bottom y value here is g of x. So what's the distance from the bottom one up to the top one? It's the top one minus the bottom one, right? 10 minus 7 is 3, means it's 3 to get from 7 up to 10. So this is the area, the distance between the top function and the bottom function. So we're always going to have like a top and bottom like this, and the main thing is just that I want to like write down a positive number right here. Like I want f of x to be larger than g of x is the main thing. If I had some scenario, if it's like this, then this is going to be my top, and this is going to be my bottom. And again, that's just to make this formula give you like a positive number here. Sometimes it's not super obvious. Like for example, we could have like something like this. So there's two functions, but like which one's the top and bottom sort of changes, right? So we can handle that too, but it'll involve like chopping it up into different segments where there's a clear top and a bottom. But as long as you can find a segment where there's a top and a bottom, then we're good. Okay, so here's top minus bottom, and I'm going to kind of say that out loud sometimes. That's kind of a good thing to have in your head, top minus bottom. Okay, so that's the area of one of these little rectangles, and we know that if we wanted the total area, we could do like a Riemann sum. I'm not going to like write the whole thing super clearly, but basically like we're doing the heights of the rectangles. I probably should have like xi's here or something, times delta x, probably write a limit, right, something, something, something. So we could go through the details of doing it that way, but the upshot is that we already know what a Riemann sum does. It creates a definite integral. and the function that's going to be inside our integral is going to turn out just to be this guy, the area of one of these rectangles. So let's do f of x minus g of x. So like before, if you just have integral f of x dx, like these little adding up a bunch of small things that I mentioned before, the y values here are like the small things. So that I can think of this as like add up a bunch of y values. Whereas this new one, I can the small things are this integrand. So I want to think of, okay, add up a bunch of numbers, but these numbers are representing the heights of these vertical lines. Or if you imagine the dx as like a little bit of width, then it's the height times that width. With that interpretation, height times width, I should really write parentheses here. But we already kind of know to just kind of keep the dx separate, so people don't usually write it, even though it's a little confusing. Okay, so the only thing missing here is the bounds. Well, what are the bounds? There's something, a to b. Where do I start integrating and where do I stop integrating? If I look over here, I probably want to get, so it would depend on what the problem said. The problem says the region bounded by the graphs. So even though there's like other region out here that is maybe touching the graphs, there's only one region which is bounded by the graphs, meaning like a finite area. If I imagine zooming out on that graph, it would look something like this, right? And so here's G, here's F. So there's other region out here, right? There's it may be even touching both the graphs, but we're not going to be interested in that. We're interested in the finite region that's in between the two graphs. So that's usually pretty clear from how the problem's stated, but sometimes you have to read it carefully. This word bounded, you're going to use to mean like a finite area between the graphs. Okay, yeah. So the starting point for our integration is actually going to be whatever the x value is right here. That the first place where they intersect. The end point of the integration is going to be this x value called b. That's the where they intersect on the right hand side. So the one kind of algebra extra wrinkle that we have to do with these problems that we didn't have to do before is we have to do a little bit of algebra to figure out what a and b are, what these bounds are. It's not too bad. It's kind of the same thing every time, but you always have to remember that there's this extra algebra step that you have to do. So how do we do it? Well, remember, just if I want to find where two functions intersect, in general, you can set the equations, set the y values equal to each other, right? So I can say set the left function, f of x, equal to the right function, and solve for x. This is just a general strategy for intersecting two curves, finding the x values where two curves intersect. And when I write this, set f of x equal g of x, I mean use the formula for f of x and set it equal to the formula for g of x. Right? When we write this, f of x equals, I'm saying wherever, like f of x is this. So this is just short for saying set the two equations, the functions, the formula is equal. It's just, if I write it this way, I'm kind of saying it generically without talking about a specific function. In our case, we have a specific function. So f is 5 minus x squared. G is x squared minus 3. So that's the algebra I have to do. I have to solve this for x. Whatever x value I get, I'm going to get two. Actually, we'll see. One of them is going to be a, and one of them is going to be b. So that's what we have to do. Okay, so let's do some algebra. It's good just to kind of collect all the same type of stuff on the side. So I'm going to add 3 over 8 minus x squared equals x squared. I'm going to go ahead and add the x squared over. 8 equals 2 x squared. I can divide by 2. 4 equals x squared. And x is going to be plus or minus 2. So the plus or minus is super important here. it's always important when you're solving quadratics, but it's especially important when you're doing this kind of problem because, like we can see in the picture, that there's going to be two answers. Like we know there will be two answers. The fact that there are two corresponds exactly to the fact that the algebra is giving us two answers. So there's a tight connection between the algebra and the geometry. So we just learned that A and B are actually -2 and 2. So those are the numbers we can plug in. So let's go ahead and write down our integral here. So this is going to become -2 to 2. I can go ahead and plug in our functions. So f is 5 minus x squared. It's good to put parentheses right there, just to keep the functions separate. And then g is x squared minus 3, and we have dx. Okay, so that's pretty much exactly the integral we'd have to do to set up to find the area. We'll simplify it and actually get the end number in a minute, but just like conceptually, that integral will find the area between the curves. If there was a test problem that said like set up the integral that would compute the area between the curves, you would just have to write this down, and that would be good enough. Yeah, so let's solve the integral. We should simplify the integrand a bit. I have 5 minus -3, so I'm going to get 8 here. And I have -x squared minus x squared, so that's minus 2x squared. Nice. And I still have my bounds here. And we have dx. And this one's pretty easy. We just do power rule. So 8 goes to 8x. This is going to go to -2/3 x cubed. And then we can plug our numbers in, 2 and -2. Yes, just to get a final answer, parentheses, so this is 16, so I'm plugging in the 2 to the 8x, minus 2/3 of whatever 2 to the 3 is, which is also 16. So that's the first part. And then minus the second part, plug in -2, be -16, and then minus, plug in -2. This will be 16, but careful, it'll actually be -16, because I have -2 times -2 times -2, so that's negative altogether. I already have this minus sign in front of the 2/3, so I can just make it a plus and write the 16 there. So it's very easy to mess up there, so just be careful. Okay, and then this is some number. I guess we can get the number. We'll have 16 and then plus 16. That's from here and here, it's 32. And then this fraction, this is 2 times 16, that's 32 over 3. And then the same fraction over here, minus 2 times 16. So actually I didn't have to compute that. Oh no, I did, because they're both minus signs. If one was plus and one was minus, then they'd be gone. So this is 32 minus 64 over 3, and that's a number. So you can get down to the actual final arithmetic part, and then it's hard. If you want to do this, so just change the 32 to have it over 3 in the bottom. The cost is you have to multiply by 3 up top. That's legal. And then you can subtract 64. You can also use a calculator. This will be 96 minus 64, and then that's a number. I think it's 22. No, 32. 90. Yeah, 32 over 3. So you get a number. 10 and 2/3. 10.66 if you like. Okay, so we can get the area between the curve, and you can even get the number if you combine fractions. By the way, I like to show the arithmetic here in the videos just because I think it's good to be able to do it if you need to, but it's totally fine to use a calculator for that kind of thing as well. But it's good practice. Okay, so just recap to find the area between two curves. Basically, we just write down the integral of top curve minus bottom curve. We got to do our bounds, so we have to solve for the intersection of the two curves to get the bounds. And that means set the equations equal and solve for x. Cool. So pretty straightforward. let's just see. There's the wrinkles come up with this when you have slightly more complicated geometry going on. So like here, it was just nice that it was just directly one curve, top curve, bottom curve, intersection. That's it. But like with this example I was drawing on the right, sometimes it gets tricky. So let's look at this one. Find the area bounded by the graphs y equals x cubed and y equals x plus 6. So y equals x cubed, you can graph it, it'll look something like this. And y equals x plus 6, it'll look something like this. By the way, it's always pretty much, you should always draw a picture. Like, it's kind of hard to tell just by looking at the equations what the shape is going to look like, unless you're like really familiar with them. So it's always fine to use graph calculator or Desmos or something to find what the picture looks like, and then you'll know what you have to do. On like an exam question, I'll usually put a picture in. Okay, there's one important detail here, which is that this is bounded by 3 things actually. This y equals x cubed, y equals x plus 6, and also the x-axis. So that means that this, right, those are 3 sort of equations. By the way, the x-axis I could call the equation y equals 0 if I wanted. So I want a region that touches all 3 of those equations. So like I don't want this region, because that only touches the cubic, but and the axis, I guess, but it doesn't touch like the other one. So here you actually want this region. So it's sort of in the middle of all the curves. It touches all 3 of them. In particular, you don't want to go like down here, because this x-axis is like blocking off your region. So this is a little bit of interpretation, like you have to read exactly what they mean, but if they say bounded by the graphs of some things and an axis, that's what they mean. So you kind of get used to that as you do examples. Okay, so how do we do this? Well, the main thing to think about here is that we always want top and bottom function, top minus bottom function. Sometimes the top or bottom function can change partway through. So here, imagine kind of scanning your eye from left to right. As we go from left to right, firstly, the straight line intersects the axis here, and then we get y equals 0, just the x-axis for a while, as like the bottom function. Over this stretch, the top function is the x plus 6 the whole time. But then it changes, right? Like right here, at the y-axis, suddenly it changes. All along this part of the curve, this part of the region, the top function is still x plus 6, but now the bottom function has changed. The bottom function is the cubic part. So what functions the top and what functions the bottom can shift partway through, and that's okay. It just means we have to break our problem up into 2 integrals. We're going to have one integral for this region and one integral for this region. Because on the left region, there's a consistent top and bottom. On the right region, there's a consistent top and bottom, but they're different from each other. So we just write down 2 integrals. So for the left one, we want to do top function, that's x plus 6, minus the bottom function. Again, the x-axis is really like y equals 0. So I could write minus 0, right? This was like y equals, this was like y equals. Okay. And dx. And then we're going to add plus, right? I just do the left region plus the right region. I'm going to do an integral. This time the top function is x plus 6, and the bottom function is x cubed. You can put it in parentheses if you want to. Okay, so the only thing really left to do here is figure out the bounds. Sometimes it's a little bit tricky, but we can just think as we go from left to right here, right? We know that first we hit this point, which I'll call that A for a second. That's the beginning, the first place of intersection. And then we hit 0 here. So we have to like maybe magically know that 0 is the place where the bottom function changes from being the axis to the cubic. But you can usually kind of guess that from the picture. You could technically do some algebra to solve for that, but I'm going to skip that. And then we kind of end at this point, right? So the x value there is, I'll call it b. So we know we're going to go from a to 0, and then from 0 up to b. We just have to figure out what a and b are. Okay, so that's just a little algebra. So for a, I want to intersect, right? To find a, I'm going to intersect x plus 6 and like y equals x plus 6 and y equals 0, right? I want to see where the line intersects the axis. For b, I'm going to intersect the line function with my cubic function. So let's do this one first. This one's really easy. I just write x plus 6 equals 0, solve for x. Great, negative 6. So I'm going to go negative 6 to 0. Just copy this stuff, right? Actually, let's just write down, because we can simplify as we go, right? X plus 6. And this one is x plus 6 minus x cubed. Okay, and then for b, we just set these equal to each other. X plus 6 equals x cubed. So x cubed minus x minus 6 equals 0. You don't have to do this, but it's a good idea to kind of write it on the right side there. Actually, let's pause on that. If we look back at the original equation, so this is actually, maybe this was a bad example for me. This is actually, so sometimes when you try to do this algebra to solve for where they intersect, sometimes the algebra is actually a little bit hard. Because of the cube here, you can't, it's hard to factor this, right? X cubed, like I could write this. It's hard to think of like how I would factor that. So this would be a good case of you can kind of use the graph to help you guess and then maybe check. In this case, if we graph this, you will see that, like on Desmos, you'll see that this looks like it's about around 2. And if we look at our equation, I could check, does 2 work? If I do 2 plus 6 versus 2 cubed, right, plugging it into left and right, this is 8, and this is also 8. So that works. So 8 is actually a solution to this. Yeah, so the intent is to solve this. I think I picked an equation that was too hard to solve by hand, so that's my bad. But on homework and stuff, it'll be stuff you can do. But you can sort of guess and check sometimes also, if you really have to. So B is going to be 2. We're going to go up to 2. Okay. So yeah, we found the area between our curves. We set up the integral. Again, this integral is the setup. If I just asked set it up, that would be it. To actually finish the problem, we'd want to get a number, finish the integral. So I think I'm going to skip that here and let you try that if you want to. But it's pretty straightforward, right? You just do like x cubed over 2, 6x, blah, blah, blah. And then you put the numbers in. Okay, cool. So something else that comes up when you're into finding the area between curves like this is sometimes it's easier to imagine turning the graph on its side. So let's look at an example of that. Here we have two curves, x equals y squared and x equals 2y plus 1. So if you go to a graphing calculator or Desmos and you type this in, you'll see the cubic one gives you something like this, or the square one gives you something like this, and then the straight line one gives you something like this. So the area between those two curves is sort of this region here. So you might not have seen this a lot before, but it's totally possible to write down equations like x equals y squared. There's nothing that stops you from being y equals. It just means you're thinking of like x as a function of y. You're thinking of y as the input. So like I pick an input, and then I square that input to get an x value, and that x value is sort of my output. But I'm graphing the output as my x value, where the input is my y value. It's a little weird, but it's totally possible. Sometimes you can rearrange between those two perspectives. For example, this second equation here, I could algebra this, x minus 1 equals 2y, and then y equals x minus 1 over 2. That formula now reads like a function, y as a function of x. The graph would look exactly the same. So if it's possible to rearrange it, the graph will look the same. So they're just like two ways to talk about the function. Remember, the function is really the association between inputs and outputs. The graph of a function is really just a way to visualize that. So with this linear equation, the x equals 2y plus 1, it's legit to think of the line itself as like the relationship between the two variables, and I could phrase that as one's the input, the other one's the output, or the other way around. You will find that it's harder to do that for some equations. For example, if I do the x equals y squared, right, if I try to solve this for y, your math teacher says you're supposed to say plus or minus square root of x. And that's true, because both of these, the positive and negative, would satisfy the equation. For example, if I pick y equals 2 as an input, x would be y squared, which is 2 squared, which is 4. So one of the points on the graph better be 4 comma 2, where x is 4 and y is 2. So that satisfies, this satisfies the original equation. But you will find that if I do 4 comma negative 2, since negative 2 squared is also 4, this one also satisfies the original equation. They both do. And that's sort of reflected in this formula, saying that, if you give me a y value, if I give you 4, what's the x value? Well, it could be 2 or negative 2. Both of those would satisfy it. And visually on the graph, that's kind of reflecting the fact that there's this top branch, the plus square root of x, y equals plus square root of x, and then this bottom branch, y equals minus square root of x. And so there's really two, if I write y as a function of x, I have to express this as sort of just two separate functions, this function and this function. There's no single function which captures that entire relationship because of the vertical line thing, right? I need to have a unique output for each input. So depending on the exact formulas, it can be impossible or at least tricky to try to rearrange it like that. This is actually the main reason you would, So that's just kind of an aside about these functions, but it's going to be relevant for us. In particular, if I just had this geometric thing and I was trying to describe it, it might seem a little more natural or easier to write it this way, because I don't have to worry about this plus or minus square root thing. I just have this nice relationship. And in particular, it'd be really cool to say, well, let's just integrate dy, with respect to y, meaning between these 2 points, I move along the y-axis from here up to here, and all along that y-axis I count up slices. What slices do I count? Maybe I count these horizontal slices like this, just as well as the vertical slices from before. If I add up a bunch of horizontal slices, conceptually, that will also get you the area. And it might be an easier way to think about the area if, part of the graph is described by these equations that actually have y's in them. Right? If I formulate my lines, my curves, as functions of y, then if I want to integrate them dy like this, I can write down their functions with y's in them. So here, the top function, right, the larger x values over my region are coming from this function, x equals 2y plus 1. And these bottom values, meaning the lower x values as a function of y, are coming from here. So I can integrate this dy by using the equations, taking the parts that have y in them. Right, I'm going from x equals 2y plus 1 as my top function, minus x equals y squared as my bottom function. And for my a and b, I'll be going from the first point as I move on this y-axis to the second point. So it's a little weird. You kind of have to turn your head sideways, but it's often useful to integrate this way. Notice for this question, if we were trying to integrate it the other way, if we were trying to do it dx, it would be kind of a pain because right, my top and bottom function changes partway through. Probably around here, right? To the left of the dotted line, the top function, and then the bottom function, and then to the right of the dotted line, here's the top function, here's the bottom function. So we'd have to do two integrals. The integral on the left would be kind of annoying because the top function would be square root of x, and the bottom function would be, well, negative square root of x, right? Because that's that lower branch. The second integral would be still root x as the top function, and then minus what? Minus this straight line function, but I have to write it in terms of x, which means I would need this guy. So, maybe that looks like an integral we could do. It doesn't look that bad, but it's still kind of a little more work, maybe, than doing it this way. It will turn out also, you might see in some examples, that sometimes it's actually impossible to solve for one variable. In this case, it was awkward to solve for the other variable because of the square root thing, but there are going to be times, something like this maybe. It turns out that it's not even possible to solve this for y equals, and so you would have to integrate this one dy. Cool. Okay, so yeah, here's our integral. Again, we have to find a and b, and again, that's just intersecting our functions. So here, I'm going to intersect, and since I'm working with the functions in terms of y, it's fine just to keep doing that. That makes the most sense. I want to set 2y plus 1 equal to y squared, and then do some algebra. It would technically work if we continued to do it dx. We'd have to set the line, which uses this formula, equal to the curve, and it'd be annoying because there's these 2 points, and they're actually like two different functions. The top point lies on the function positive root x, and the bottom point lies in the function negative root x. So we'd have to solve both of these. And because of the square root, that looks annoying, right? So you could do that as well, but it's a little more awkward. Let's just finish this one up. Y squared minus 2y minus 1. Notice I'm just by default putting all the stuff on one side. It's easier because now I can just think, oh, this is a quadratic. Maybe I have a way to do quadratics, right? Here we want to think of either factor it or use quadratic formula. You always want to do that. Can I factor it? I need two numbers that multiply to -1 and add up to -2. I think we're not going to get ones, so we can always quadratic formula. So y is going to be, I might be wrong, it's hard to do math and talk at the same time, but let's do quadratic formula. So b squared, that's 4, minus 4ac, so -1 over 2. So this is 4 plus 4, so this is 8, this is 2, and that's going to turn out to be a number. We can try to simplify it. A good thing to do with this root, 8 is really 4 times 2, right? When you square root, you can square root each of the parts and multiply them together. So we get root 4 root 2 over 2. So this root 4 is actually a 2, so I can cancel 2 out of everything. I'm going to get 1 plus or minus root 2. Okay, so I was not incorrect. It is not possible to factor this. You don't get a whole number here. So you can't factor it with whole numbers. You can factor it into this if you want to. Okay, so sometimes you have to do a little algebra, and you might have to do quadratic formula. Cool. So plus or minus means we get 2 answers, right? So our A is going to be the negative 1. 1 minus... Actually, it's good to think through why that's the case, right? If we look back up to our graph, right, remember these are y values. So like 1 plus or minus means like 1 is in the middle somewhere, like here. And then 1 plus something will be up here, and 1 minus something will be down here. And if you might know root 2 is like 1.1 something. It's bigger than 1. So 1 minus root 2 will be negative. So that makes sense. So our lower bound is going to be 1 minus root 2 up to 1 plus root 2. And we'll have, just rearranging a little bit, we'll have our equation from before, which you could do. Okay, cool. Okay, so I think that's most of what I wanted to say about 6.1. So that's all area between two curves and sort of introducing the idea of using definite integrals to find volumes, masses, work. Next lecture, I will talk about volumes by slicing, which is another way to do volumes. But I'll pause this one for now and see you next time.